So, welcome to the next module of this course, which will be final module on mathematical preliminaries. Okay. So, there are 3 lectures planned in this module, and as you can see, these lectures will cover very important topics of linearization, directional derivative and tensor analysis, and also we will devote some time on working out some examples, so that you should be able to understand the theory much better. So, this is the content of this module. The first one is linearization and directional derivative, followed by tensor analysis, and then finally, we will look into the worked out examples, okay, to help you with the theory part. So, coming to the first topic. So, these nonlinear problems will invariably result in nonlinear equations, okay, and these nonlinear equations have to be solved by linearizing. Okay. That is what I have underlined here. Okay. This term over here, which is very important, is linearization. Okay. So, you have to linearize these nonlinear equations. Okay. And then once you have linearized these nonlinear equations, you have to solve these equations iteratively using a suitable technique. Okay. And you have to do this until you have found out the solution. Okay. So, one of the most popular technique is Newton-Raphson method. Okay. Obviously, there are other techniques to solve nonlinear equations, where you need not use any iteration. You can just keep on solving the equations. Okay. So, you linearize, and then you can, without employing Newton-Raphson method, you can just solve that, but we will concentrate on method which use iterations to solve the system of nonlinear equations, okay, and will specifically focus only on Newton-Raphson method. Okay. So, to get the accurate solution for your system of nonlinear equation, you have to have a very correct linearization. Okay. So, correct linearization is must for getting accurate solutions. What it means is, if you do not linearize properly, it might happen that you might get a solution, but it will take much longer to get the solution. Longer means in terms of the computational time, okay, or in the worst case you will not get any solution at all. Okay. So, it is very essential that a correct linearization, okay, is carried out for Newton-Raphson method to work nicely. Okay. So, before we begin with system of nonlinear equation, let us first start with exploring the solution of single variable nonlinear equation, which is, we have written here, f of x equal to 0, x is a variable. Okay. Now, our equation is f of x, and now we want to solve this equation. What it means is, we want to get the roots of this equation. Okay. So, we want to solve for those values of x for which f of x is equal to 0. So, before starting the mathematical details, we first look into the graphical interpretation of how the solution for a nonlinear equation is obtained using Newton-Raphson method. So, as you can see here, we have plotted a general function f of x, which is shown here as this yellow line, okay, and the point at which this function cuts the x axis, okay, here. That is where your solution lies. Okay. So, f of x equal to 0 is this point where the yellow curve intersects the x axis. Okay. So, now to solve this equation, the first thing that one should have is an initial guess. Okay. Initial guess means you do not have an idea about the solution, but you have some idea in which range the solution will lie. Okay. So, you have some idea of the solution. So, say x 0, say this is the initial guess that you start with, and then as you know x 0, you know the value of f of x 0. Okay. Now, you can see f of x 0 is not equal to 0. Okay. So, that means x 0 is not the solution. So, what do you do? What we do next is we make a tangent at this point. Let us call this point as A. Okay. So, this red line is a tangent to the yellow curve at point A, and then we know the slope of the line, red line. Okay. That is the derivative. Okay. Derivative of the curve at x 0, that is f dash x 0. Okay. And now, we know this point also, the coordinates of this point. So, we know the equation of red line, and using that we can find out where this red line cuts the x axis. Let us say this point is x 1. Okay. Now, again we can compute the value of the function at x 1. Okay. Say this is the value of function f of x 1. Okay. Now, we notice that although the value of the function is still not 0, but this value of the function f of x 1 is less than f of x 0, okay, which means our new approximation of the solution x 1, okay, has reduced the value of the function. Okay. So, we are approaching in the correct direction. So, now since we are still not reached 0, then what we do? We follow the previous procedure at say this point is B. Now, again at point P we make a tangent, okay, and knowing the slope of the red line and the coordinates of point B, we can compute the intersection of the red line with the x axis. Let us say it cuts at value x equal to x 2. Okay. Now, again I can check the value of the function f of x 2. Okay. So, I can check the value of the function f of x 2, and you can see here that again f of x 2 is not equal to 0, but obviously f of x 2, the magnitude or the value is less than f of x 1. Okay. So, again we are reducing the value of the function. Okay. So on we keep on repeating this. So, we go to x 3, x 4 and we keep on doing this till we reach our point of interest, which is this solution. Okay. F at say nth step we reach the solution where f of x n is equal to 0. Okay. So, as soon as we reach f of x n equal to 0, we know that x n is our solution. Okay. So, that this graphical illustration shows how the Newton-Raphson procedure actually works. Okay. Now, the thing to note is when you are applying Newton-Raphson procedure over computer, you may not actually get 0. Okay. You may get a very small number, okay, maybe 10 is power minus 9, 10 is power minus 10 or something like that, but you will not actually get 0. Okay. So, we have certain criteria. We say that whenever say f of x k becomes less than say some value epsilon tall. tol is for tolerance. Okay. So, when the magnitude of the function at kth point x k is less than our specified tolerance. Okay. So, this tolerance has to be given by the user who is using this procedure, and whenever this value becomes less than this tolerance, we say that our solution is x k. Okay. Now, the important point to note about this Newton-Raphson procedure is, if you are nearer to the root, okay, as you go nearer and nearer to the root, that is, as you approach the solution, the rate at which the convergence is achieved is quadratic. Okay. So, if you are far away from the root, say x 0 was far away from the solution that we were seeking, then initially the convergence will never be quadratic, but it might be linear, what is called linear. Okay. But as we approach towards the solution, the last few steps of Newton-Raphson will actually show you that it converges what is called quadratically. Okay. So, that is one of the feature of Newton-Raphson procedure, and if you have computed your tangents, okay, that is slope of this red line, if you have computed this tangent accurately, then this quadratic convergence is guaranteed. However, you will notice that even if, say for example, at point B, you did not calculate the tangent accurately and say you calculated something like this, then instead of reaching x 2, you would have reached a point x 2 dash, but still you have moved closer to the root, okay, or the solution x n. Okay. So, even if you have a wrong tangent, it does not mean that you will not get a solution. Okay. You might still be able to get the solution, but the rate at which you will approach the solution will not be quadratic. You will take much more number of steps to achieve the solution, that you have to remember. So, the fact that I mentioned in the previous slide, so to get the correct and accurate solution, okay, and ensure the quadratic convergence of Newton-Raphson procedure, it is necessary that you calculate the tangents of this Newton-Raphson procedure very accurately. So, that it means the linearization has been done very accurately. Okay. Next, we move to the mathematical framework for the graphical procedure that we have just discussed. Okay. So, now what we do, we start by expanding this function, okay, f of x using Taylor series about our initial guess x 0. Okay. So, equation 1 here shows that Taylor series expansion of the function about point x 0. Okay. So, f of x is equal to f of x 0 plus d of df by dx evaluated at x equal to x 0 into x minus x 0 plus 1 by 2 d square f by dx square evaluated at x equal to x 0 into x minus x 0 the whole square plus and so on. You will have quadratic curve, you will have quartic term like this. Okay. Now, if you denote x minus x 0 as u, which means x is x 0 plus u, and if you use this in equation 1, then we can rewrite equation 1 as f of x 0 plus u equal to f of x 0 plus df by dx evaluated at x equal to x 0 into u plus 1 by 2 d square f by dx square x equal to x 0 evaluated at x equal to x 0 into u square plus higher order terms. Okay. Now, the question you might raise at this point, or your doubt might come, why we have chosen this symbol u, okay? Because in undergraduate books on numerical analysis, mostly this term h or the symbol h is used, but we have specifically chosen u because as we move later on in this course, u will come to signify displacements. Okay. So, if you use the symbol here, it is much easier to understand later, because instead of the scalar u will have vector u, which will be a bolt. So, it has become very easy to understand, much easier to understand. Okay. So, now you get this equation 2 over here. Now, what we do is we linearize equation 2. Okay. So, how do we linearize equation 2? You would have seen that the first term on the right hand side is a fixed value. Okay. It is the value of the function at x 0. The second term, it is a linear function in u. Okay. It is a linear function in u, because u has a power of 1. This df by dx evaluated at x equal to x 0 is a also known value, but u is unknown for you right now. Similarly, the third term is a quadratic term, okay, where u is u square, therefore, it is a nonlinear term in u square. So, all the terms beyond this linear term are nonlinear terms, okay, nonlinear in u, they are all nonlinear in u. So, to linearize, what we do is we neglect the higher order terms, okay, terms containing u square, u cube and henceforth, that we neglect in equation 2, and then what we get is the left hand side will be approximately, that is why you see instead of the equal sign, now we have the approximation sign. So, f of x 0 plus u will be approximately equal to f of x 0 plus df by dx evaluated at x equal to x 0 into u, and all the higher order terms which were here have been neglected. Okay. We have all neglected the higher order terms. Okay. So, this second term over on the right hand side is what is called the linearized increment in f of x at x 0. So, this is the term in this bracket or this box, red box, is called the linearized increment in f x at x 0. Okay. So, this term inside the red bracket is usually denoted by d, capital D, f of x 0, and then there is square bracket u equal to df by ds x equal to x 0 into u, which from the third equation is nothing but f of x 0 plus u minus f of x 0. Okay. So, this is a standard convention, which is I have written here, this is standard convention. And how do you compute this d of f x 0 at square bracket u? So, this square bracket does not mean that x 0 is multiplied by u, okay. It has a different meaning. Okay. So, whenever in this course we use square bracket, it does not mean you have to open up the bracket, there is a special meaning for these kind of brackets. Okay. So, the way you compute this linearized increment, which is this term over here, is as follows. Okay. So, what you do? You take your function and replace x by x 0 plus eta times u. Okay. So, if you have your function in x, what you do? You substitute x equal to x 0 plus eta times u, okay. And then what you do is take the derivative of that function with respect to eta, and then finally substitute eta equal to 0. Once you have done this, you will get the linearized increment of f of x at x 0. Okay. So, you have to note that this symbol d of f of x 0 at u denotes a derivative, and the way it is read is directional derivative of f at x 0 in the direction u. Okay. So, whenever you see this term d of f x 0 at u, okay, it is read as directional derivative of f at x 0 in the direction u. So, now we can now set up the Newton-Raphson iterative procedure using equation 3. Okay. So, what was equation 3? That was equation 3. Okay. So, to set up Newton-Raphson procedure, the left hand side of equation 3 is set to 0, and instead of x equal to x 0, we put x equal to x k. So, we have f of x k plus the directional derivative of the function at x k evaluated in the direction u, where k goes from 1 0 1 to 3. Okay. So, when k is 0, you have f of x 0 plus d f of x 0 at direction u. When k is 1, you have f of x 1 plus d f of x 1 in the direction u equal to 0, like so on. And then what is x k plus 1? The new solution x k plus 1 will be simply x k plus u, where k goes from 1 to u. Okay. In this way, you can set up the Newton-Raphson procedure. So, what we do? We start with k equal to 0, k equal to 0, you have x 0. Okay. So, now you compute u using this formula. Okay. So, this formula you can obtain from equation number 3. So, u will be minus of df by dx evaluated at x equal to x k raised to power minus 1. Okay. So, there is a square bracket. So, let me just make it a other kind of bracket. Okay. Because I told square bracket will have a special meaning. Okay. So, you compute df by dx at x equal to x k, okay. Take the negative of it, take the inverse and then multiply it by f of x k. You will get the value of u. Okay. So, at k equal to 0, x 1 will be x of x 0 plus u. Then you recompute for x 2, x 3 and so hence so on, and you stop when f of x k becomes less than a tolerance value. Okay. So, the important point to note is the convergence will be quadratic near the solution, provided the directional derivative of the function at x 0 or say x k is accurately computed. Okay. If you have computed your directional derivative accurately, it is guaranteed that you will converge quadratically near the solution. Okay. Next, we move towards setting up the Newton-Raphson procedure for a set of general nonlinear equations which are given by this g of x equal to 0. Now, you notice instead of scalars, now we have bold symbols. Scalars were simple non-bold symbols. Now, we have bold symbols, and where this function g of x may represent a system of nonlinear algebraic equation as one would get in finite element method, or they may represent nonlinear differential equation where the unknown x can be functions. Okay. So, equation 9 is very general right now. It can represent system of nonlinear algebraic equations, or it may also represent nonlinear differential equations. Okay. So, therefore, x represents a list of unknown variables or functions. Therefore, equation 9 represents the most general form of nonlinear equations. Okay. That is the most general form, and when we go into worked out examples, you will be able to see it more clearly. Okay. Now, we want to solve this general nonlinear equation. Okay. So, we again, as was in the case for function of single variable, we take an initial guess x 0 and we take an increment u. Okay. Now, we have x 0 which is bold, which is some scalar, and increment u which is also bold, okay, which means okay, it is a vector, sorry, x 0 is a vector. Okay. So, now we can generate a new solution x as x 0 plus u, with the hope that when we do x 0 plus u, okay, we will be getting closer to the solution. Okay. So, Now, the problem right now is when we try to extend the previous procedure, okay, which we did for a single nonlinear equation to this general nonlinear equation given by equation 9 over here, it is not clearly known how will you take the derivative of a complicated function g of x. So, to do this, what we do is we introduce a artificial parameter called eta. Remember, our initial guess is x 0 and say we want to move in the direction u, arbitrary direction u, that will take us closer to the solution. So, in a way we know x 0, u is what we want to find out. So, what we do is we rewrite our given nonlinear equation g of x in terms of eta as given by equation 11. So, we substitute instead of x, we substitute x 0 plus eta u. So, what we get is a nonlinear equation solely in terms of eta, which is on the left hand side of equation 11. So, for one variable nonlinear equation, this would be like what is shown in equation 12. Now, what we do is we take the Taylor series expansion of the nonlinear function g of eta in equation 11 at x 0 and then setting eta equal to 0. So, this is the Taylor series expansion of g of eta about x equal to x 0 and setting. So, g of eta is g of 0 plus dg by d eta evaluated eta equal to 0 into eta plus 1 by 2 d square g by d eta square evaluated at eta equal to 0 into eta square plus higher order term. Again you can see the second term is a linear term in eta, the third term is a nonlinear term in eta. The first term obviously is known at eta equal to 0. So, eta equal to 0 is basically x equal to x 0. Now, we can introduce our definition g of eta was g of x 0 plus eta u. So, when we introduce this in equation number 13, which was there on the previous slide, we can write g of x 0 plus eta u as g of x 0 plus eta d by d eta evaluated eta equal to 0 of g x 0 plus eta u plus eta square by 2 d square by d eta square of g x 0 plus eta u evaluated at eta equal to 0 plus so on. Now, we as we did in a single nonlinear equation case will neglect these higher order terms. What we will do is we will neglect these higher order terms. So, if you neglect the higher order terms, so the left hand side will be approximately equal to g of x 0 plus the linear term in eta. Now, the problem here is we have unknown eta and we also have unknown u, the direction in which we want to get the solution. It is the direction, u is the direction which will take us closer to the solution. Because eta was an artificial parameter which was only used to perform the derivative. So, we can simply eliminate eta from our equation number 15 by just substituting eta equal to 1. So, when we substitute eta equal to 1, so this eta will be equal to 1 and this eta will be equal to 1. So, the eta here, so this is no eta in this term because eta has been substituted with 0. So, there is no eta here. So, what we get here is this equation 16. Now, the second term on the right hand side of equation 16 is what is identified to be the directional derivative of x 0 of g, directional derivative of g of x 0 at x 0 in the direction of u, and this is written as dg x 0 in u, dg x 0 evaluated in the direction u, and this can be calculated using following expression on the right hand side. Okay. So, you write the system of, you write the nonlinear equations by substituting x as x 0 plus eta u. Okay. Then you take the derivative of that with respect to eta, and then finally, you substitute eta equal to 0. So, this will lead to, this will give you the directional derivative of g at x 0 in the direction u. Okay. So, you have to note that u can be either a list of variable or a set of functions. Okay. So, therefore, when we are using this term in the direction of, right now is a very general term at the moment in terms of its interpretation. Okay. So, if you ask what is direction in the direction of a function, it does not actually mean anything. That is why when we say in the direction of, therefore, its meaning is very general at the moment. Okay. Now, when you use equation number 17 in equation 16 on the right hand side, in right hand side of equation 16, we substitute, we will get the new approximation of the function value g of x 0 plus u as the old value of nonlinear equations at x 0 plus a linearized approximation dg evaluated at x 0 in the direction u. Okay. Now, if you set the left hand side equal to 0, then you get g of x 0 plus directional derivative of g at x 0 in the direction u equal to 0. Okay. Now, this directional derivative of g at x 0 in the direction u is a linear function, is linear in u. Okay. Okay. So, this equation 19 is a linear equation with respect to u. So, you can basically solve for u, and this will help you set up the Newton-Raphson procedure. Okay. So, like previously we replace x 0 by x k, a general kth step, and we write, we want to solve dg, okay, directional derivative of g at x k in the direction u will be equal to minus of g evaluated at x k, where k goes from 1 to 0, 1, 2, 3, and then the new solution x k plus 1 will be the old solution x k plus the direction u which has been computed in from equation number 20. Okay. And then you iterate. Okay. So, you start with x equal to 0, you start with k equal to 0, sorry, and then you have x 0, you compute u, get the value of x 1, you go back, check the convergence criteria, and if the criteria is not fulfilled, then you compute x 1, x 2, okay, then you again compute u, and then compute x 2 as x 1 plus u, and you keep on doing this till you achieve your convergence criteria. Okay. So, this establishes the Newton-Raphson procedure for nonlinear equations given by g of x equal to 0. Okay. So, there are some properties of directional derivative which will be needed in the worked out examples that we will do, and we will revise these three properties. The first one is, if the given nonlinear equations can be written as addition, okay, or the sum of two set of nonlinear equations g 1 x plus g 2 x, then the directional derivative of g at x 0 in the direction u will be the directional derivative of g 1 at x 0 in the direction u plus the directional derivative of g 2 at x 0 in the direction u. Okay. The next is, if you can write your given nonlinear equation as a product of two functions g 1 and g 2. So, g 1 x into g 2 of x, then the directional derivative of g at x 0 in the direction u will be the directional derivative of g 1 in the direction u evaluated at x 0 times g 2 evaluated at x 0 plus g 1 at x 0 times directional derivative of g 2 at x 0 evaluated in the direction u. Now, this dot this dot that you see here, okay, again it is very general, has a very general meaning right now. I mean, it does not actually mean the multiplication. Okay. The last property is, suppose your g of x is g 1 function of g 2, which is again function of x, then the directional derivative of g at x 0 in the direction u will be nothing but the directional derivative of g 1 at g 2 evaluated at x 0 in the direction, okay, in the direction of the directional derivative of g 2 evaluated at x 0 in the direction u. Okay. So, understand it is a little bit confusing right now. So, next we will see this last property in much more detail, okay, in the next slide. Okay.